All right, divergence and curl. So this is a somewhat short section, but a rather important one. We're introducing two more operations that make up the three standard operations of vector calculus. So we learned about gradient way back in the beginning, and now we're introducing divergence and curl, and these are operations that apply to vector fields. So first, I'm putting together all of these three operations. So recall that what we defined nabla to be this vector symbolically. It's this vector of partial derivative operations. So this is just an abstract notational convenience. It doesn't have any intrinsic meaning, since, like, we're used to thinking of vectors as quantities denoting a length and a direction. This does not denote that at all. But if we give ourselves this kind of notational mnemonic, what it does for us is really useful. It allows us to remember these three operations. So gradient, curl, and divergence. I'm writing it in this order. There is a notation for it, which is like this, which is where we really are using this mnemonic. Okay, because, well, if we expand it out, then just putting nabla beside it ends up we can kind of push f into each of these components, and so now we have the partial derivatives of the function f, which is the gradient, as we are quite accustomed to at this point. With curl, we're taking the cross product of nabla with f, which, well, the cross product is this determinant, where we have these partial derivative operations. And now, well, what does that mean? Well, if we compute the determinant by expanding along the top row, the the minor corresponding to I, or the cofactor corresponding to I, is going to be the y derivative of r minus the z derivative of q, which is here. I should probably say that my component functions for f are p, q, and r. This is one of the standard conventions. This might be the first time I'm using this standard convention. I've been using f1, f2, and f3, but p, q, and r is another common set of conventions for labeling this vector field. And so if you do that, then, well, the first component, then p, q, and r are this third row, and yeah, the first component of the curl ends up being ry minus qz. The next one, remember that signs alternate, so you have a negative in front, and it's r sub x minus p sub z in parentheses. And then for the third component, you have this subdeterminant. It's q sub x minus p sub y, right there. And so that's the curl. And this is a completely separate vector field. Yeah, right. So, and then divergence. So divergence ends up being, you take nabla and you dot it with f. You're taking the dot product. So the dot product of these two vectors, vector-like things. So you end up multiplying component-wise and summing up all those products. So it's p sub x plus q sub y plus r sub z, which is right there. Now, let's kind of pay attention to the types of the inputs and outputs here. So the gradient takes in scalar functions. The curl and divergence take in vector functions, or vector fields, I should say. You might call a scalar function a scalar field. So it's gradient operates on scalar fields, whereas curl and divergence operate on vector fields. And the results, notice, so the result for gradient, as we know, is a scalar function. Okay. Curl and divergence, they actually have different types. So curl gives you a completely different vector field, but divergence ends up giving you this. Well, this is actually a scalar function, or a scalar field. Right? This is a function. It doesn't have multiple components. Okay. Uh, right. Yeah. So some terminology here. So I might use that later, I think. So if one thing that we mentioned previously was that if the vector field, if some vector field is coming from the gradient of a potential function, we call that sometimes a gradient vector field. Although more commonly, I've been calling that a conservative vector field because of the property that it conserves, say, energy. And path independence is also kind of related to that idea, but we separately had this terminology of it being called a gradient vector field. We have a similar terminology for if the vector field comes from being the curl of some other vector field. So those vector fields that arise as curls of other vector fields, those are called curl vector fields, as you might expect. Okay. Some algebraic properties of divergence curl, just kind of nice to know about. So they are both linear. So that means that if you are adding two vector fields and then taking divergence, that's the same as if you took the divergence of the vector fields independently and then you add them together. Similarly with curl for addition. And also scalar multiplication. You can pull scalars, little typo. That's supposed to be bold. You can pull scalars out of of applying divergence or of applying curl. Right? So that should seem reasonable, especially given like the definitions here. This should be reasonable that all of these properties. Okay, and here we have two quick examples of computing these things. So it's just getting used to this operation. So say you have this vector field and you're asked to take its curl. So what do? You insert things into the expression for curl. You're taking this special determinant. And here I'm sort of just making it a bit quicker to write. So instead of fully writing, I guess I'll do it off to the side. So instead of writing this, I'm just abbreviating that and saying that that is del sub x, right? So just a quick abbreviation for all of these. And so, well, you can go ahead and compute it. Let's just check this off. So for a component corresponding to I, it's going to be partial y of this function, which is just going to be 1, minus partial z of this function, which is going to be 0. Okay, so 1 minus 0 for the first component. For the second component, we have a negative in front. Main diagonal gives you 0. Anti-diagonal gives you 0, so this is going to be 0. And for the third component, corresponding to k, it's going to be partial sub x of the exponential, which is just the exponential, and then partial y of xy, which is just going to be x, so, with a minus. So there we go. And so that ends up being the resulting vector field from taking curl of f given. Next, if we're asked to take the divergence of this vector field, so, then we take the x derivative of the first function, the y derivative of the second, the z derivative of the third, which gives us that expression. You can see that's a scalar function. Okay. Now for some intuition about what these quantities are doing. So we had a intuition for what gradient does, right? Gradient is a vector pointing in the direction of steepest ascent, whose magnitude is how quickly you ascend. So we had that in the past. Now we have some other kinds of physical intuition for what these, for what curl and divergence are doing. Curl, if you take the curl of a vector field and you evaluate it at a point, that is going to give you back a vector. Okay, so it's a vector field. You plug in a point, you get back a vector that is like based at that point. That vector has a magnitude that corresponds to how quickly the vector field is rotating around this region. So if you pretend that the vector field is corresponding to like the velocity vector field of a fluid, so that it's describing the flow of the fluid, then the idea is that if you insert this paddle wheel, this shape that's here, if you put it in at this point and you have it like oriented so that it's perpendicular to the vector field, that way it just maximizes the rotation. The rotation itself is going to be the magnitude of the curl. Right? It's the magnitude of this vector, which is the curl of f evaluated at p. Okay, so that's what curl is measuring, how quickly things twist. Okay, now divergence. Divergence is it's also kind of appropriately named. So it's how quickly, I think it's quickly, how quickly things are expanding or contracting if it's negative. So when divergence is a positive quantity, and it should be the case that you then are evaluating this at a point. So this will look ugly, but it's more like you're doing divergence of the vector field f, which is a function, and then you take that function and you plug it in at a point. Right? That's gonna then give you back a number. And if that number is positive, that means that there's like an expansion going on. So if f is a vector field for the velocity of a gas, then divergence evaluated at a point is going to be the outflow of the gas. It's how fast the gas is expanding. And if it's negative at the point, then that's like how fast the gas is compressing. And of course, yeah, if the divergence is 0, then that means that it's neither compressing nor expanding near P. Terminology that may show up in the future, I'm fairly sure it won't show up in this course, but it'll then, at some point in your later classes, it'll be taken as granted that you already know this. So divergence, when divergence is positive, that's a source, right? So do I not have pictures of this? I don't have pictures of this. Okay, so you can think of like a vector field that's something like this would be a vector field that has divergence of f greater than 0. And so then this point at the origin is a source. If you flip the direction of all those arrows, then you end up with a sink, right? Where everything is pointed towards that point. The divergence of that is negative, and that is a sink. So source, sink. Okay. And if a vector field has no sources or sinks, then we can that vector field is sometimes called incompressible. So if we're talking about like realistic phenomenon, for fluids, it's generally assumed that fluids are incompressible, so they shouldn't have these kinds of things showing up. With gases, it's slightly more possible, but not with like aerodynamics considerations, because in those situations in those situations it's assumed that like air is incompressible, but you can sometimes make it appear to be compressible, like if you put it in a tube and you, I don't know, put it in a compressor. Anyway. Right, okay, more vocabulary. So this expression that the curl is equal to, the curl of some vector field f is equal to 0, sometimes this is stated as saying that f is curl free, or f is an irrotational vector field. And if in this statement here, divergence of f is equal to 0, that's sometimes said as f is divergence free, or f is an incompressible vector field. So those terminologies should make sense, right? Curl measures rotation, so it's irrotational. The curl is 0. Divergence is measuring like whether it's compressing or expanding. So if divergence is equal to 0, then it's incompressible. Is kind of sensible. Okay. Right. So now that we have these operations, divergence and curl, we can reinterpret what we've discussed about conservative vector fields. So first, let's recall that conservative vector fields are vector fields where the gradient, well, where they arise as the gradient of a potential function, where they are gradient of some potential function f, little f. So all conservative vector fields are coming from gradients of potential functions. And also, we know by Clairaut's theorem that the conservative vector fields satisfy this cross partials property. So if f is the vector field given by functions p, q, and r, then the cross partials property says that p sub y equals q sub x, that q sub z equals r sub y, and that r sub x equals p sub z. Right? All we do to construct these is that we pick two of them and we swap the variables that are corresponding to their placement, basically. So p is in the x component place, and q is in the y component place, z is in the r component place. And so when we select p and q, we're doing q sub x minus p sub y. I should really make that look more like a y. Okay. For q sub z, if we pick q and r, then we get q sub z equals r sub y. And if we pick, if we pick p and r, then it's r sub x is equal to p sub z. So that's how we get all three of these. But now that we have this operation, the curl, you can look back and notice, well, okay, it's a little bit far back, but this guy, if you set this equal, all three of these components equal to 0, you can move things around, and then you get the cross partials. You get those three equations that define the cross partials property. So that these three equations is equivalent to this one equation, that the curl of the vector field f is equal to the 0 vector, which is equal to 0. So we are able to then restate these theorems from a previous section, that if f is conservative, so originally this was stated as saying that if f is conservative, then it satisfies the cross partials property. We can rewrite that as saying if f is conservative, then the curl of f is equal to 0. And we also had this kind of a test for conservative vector fields. So the idea was that it was this implication in reverse, right? So the converse of this statement, which only holds true if your domain of your vector field is simply connected, simply connected. So meaning that it doesn't have any holes, right? So if we assume that f is a vector field on a simply connected domain, then we have the converse. Then we have what originally was said as cross partials property implies f is conservative. Now we have if the curl of f is equal to 0, then f is conservative. So it's just restating those properties, and instead focusing on this operation, the curl. Okay. Now for something that leads somewhere, but it leads far outside of the course. So the first part here is still relevant for us. The fact that there is, just as how we had gradient of curl is equal to 0, which is really what we were saying here, because what we said here is we assume that f is conservative, and f being conservative means that it's the gradient of some potential function. So this is really restating that. this is a very general statement, right? Because f, we didn't specify any particular function f, so it's any function f. We have that this holds true, right? And it turns out that there is a similar version of this relationship, but between curl and divergence. So the divergence of the curl of a vector field f is equal to 0. And that is very quick to derive. All you have to you first like compute the curl of the vector field, which ends up being this. Just from you can look at the definition, or if you just recompute it from the determinant formula, and then you take the divergence of this, and that's pretty quick. So we take the x derivatives of these, which ends up being this. You can see that we just tack on an x as a subscript because we're just taking another derivative. So these are second order derivatives. For the next component, we take a y derivative, which ends up being these two terms. And then for the z component, we take the z derivative, which is these two terms. And then per the definition of divergence, after you take these partials, you add them all together. So that's why we end up adding all three of these quantities. And you can see that there's some cancellation. Assuming Clairaut's theorem, which says that the mixed partials can, the order doesn't matter. So this q sub zx is equal to this q sub xz, but it has opposite signs, so they cancel. Same with the p's, same with the r's. And so everything cancels, and you're left with 0. That's a very straightforward proof. All right. So we have those two properties. And there's another property that I'm not going to show, which is related to this property. So we have this, which is really just, which is this statement here. So assuming that you have f be defined on a simply connected domain, then curl of f being 0 implies that f is conservative, which is this statement. F is conservative. F is the gradient of a potential function for some function f. Right. There is an analogous statement which says that if the divergence of f is 0, then f is coming from the curl of some vector field. So just you might need to pause and think about like how these two statements are analogous, but they are. And so this is where things start to get abstract, as I'm sort of saying in this heading. We take these 4 properties, which have numbers, equational numbers next to them. These 4 equations that relate the gradient, the divergence, and the curl. They can all be combined into one statement, which to really understand this statement actually requires a bit more understanding of advanced mathematics, like abstract algebra. But I'm just sort of showing it to you that these can all be encapsulated as just one statement, as just one idea, which is that this sequence, right? F, the function f, that you take the gradient of, you get to this bold f. You take the curl of, you get to this bold g, and bold g, take the divergence of, you get to this little g. So the symbols here should make sense because the bolds mean that they're vector fields, the lowercase italic means that they're functions. Right? This sequence is exact. Exactness expands out into these 4 properties. So 2 properties by looking at this pair of maps, I would say, taking the gradient, then taking the curl, is there end up being 2 properties about that. So, and I guess let me try to explain this a little bit. So, one of the properties about exactness, one of the statements about exactness, is that the composition of any 2 maps should be 0. That is one of the properties, which we see in parts 1 and 2. Gradient of curl is equal to 0 is precisely shown here. Gradient of curl equals 0. And a divergence of curl is equal to 0. or oh, have I been saying this backwards? Curl of gradient is 0. Okay, yeah. Uh, this and then this next one is to do with, you see that you take the curl, you then take the divergence. That should be 0, and that's another, like, you're composing two maps in this sequence, which equals 0. That is another part of what it means to be exact at this G here. The other half of the statement about exactness is that at each place you also have that, so I'm not going to define these words, but I'm just going to use them. The curl of this map must be the image of the previous map. So curl of this is, or kernel of this is equal to the image of that. Kernel of this is equal to the image of that. So what that actually means is precisely this statement, it turns out. So these two statements. And I'm not going to explain that any further than that. So just a nice thing to know. And I've also I've rewritten this in a slightly different way. So this might be more typical of a way to express this statement. I don't know. And this is if you're trying to be more sophisticated. I can still explain to you. It's not too bad. The C infinity means that the functions are smooth, meaning that they have infinitely many derivatives. You can keep taking derivatives and you still get nice functions. So common examples of this would be polynomials, exponential functions, sine and cosine functions. I think those are typical things that come to mind when you talk about functions that are smooth. And this notation means your function takes 3 inputs, gives back 1 output, and takes an input that is in R3, so like a vector of length 3, or a vector of dimension 3, I should say, and then its output is a scalar, right? Which is well, it is a scalar field. It is a scalar function if we sort of stick ourselves simply within dimension 3. And this one, well, you can see that, yeah, if we take input that is of dimension 3 and it gives you back output of dimension 3, that's like you're taking a vector in 3 space and you're outputting a vector in 3 space. That is like a vector field. And you can see this is the same as a vector field. This is similar to this, so this is a scalar field. And it's been slightly extended, but that's fine. Okay. And yeah, we don't need to talk about that. That is way beyond. But that's kind of where this story is leading up to. If you end up like going much further into mathematics, this is at least master's level material. So definitely not going to talk about that here. But all right.